This is the chapter on Coulomb's law. Coulomb's law explains the forces between charges. Let's start off with 2-point charges, Q1 and Q2. These point charges are separated by a distance r between them. And according to Newton's third law, suppose this charge is positive, and this is also a positive charge. The two charges repel each other. So we can say that the force of charge 1 on charge 2 is this force here. And the force of charge 2 on charge 1 is that force. According to Newton's law, these charges are equal and opposite. So we can say that the force of charge 1 on 2 is equal to the force of charge 2 on 1. And this is equal to a certain force F, which we call the electrostatic force. According to Coulomb, this electrostatic force F is proportional to the product of the two charges Q1 and Q2, and inversely proportional to their squared distance apart. The distance is r between them. We can remove the proportional symbol by putting in a constant k that way, and this constant of proportionality k is called Coulomb's constant. So k is called Coulomb's constant. The magnitude of k is equal to 8.99 times 10 to the power 9 newtons meter squared per coulomb squared. K is sometimes also written as 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. So this letter E is equal to epsilon. It's a Greek letter, epsilon. So when I say E suffix 0, that is epsilon naught. The smallest unit of charge is the elementary charge. This elementary charge E is equal to 1.6 times 10 to the power negative 19 coulombs. So when I talk of elementary charge, what I'm referring to is that every charge is an integer multiple of this elementary charge. So we can write that Q is equal to NE, where Q is in coulombs and E is the elementary charge, and N is an integer. So we can say that for an electron, E is equal to minus 1.6 times 10 to negative 19 coulombs, and for proton, E is equal to 1.6 times 10 to negative 19 coulomb. Because the electrostatic force is a vector quantity, we can add up multiple forces as follows. So let's suppose that we have multiple charges and we want to find the force on one charge. We can use the superposition principle as below. So let's say this is a point charge in that location. Let's call it Q1, a point charge Q2. Let's call this Q3, and let's say this is Q4, and we can say there's another charge here, Qn. Suppose we want to find the net force on Q4. We shall proceed as follows. So I'll draw the diagrams here. So we can say that the force of 1 on 4 is this force here. This is the force of 3 on 4, and this is the force of 2 on 4. Let's say that is F24, and then the force of N on 4 is another force this way. So we can add all these forces up to get a net force on charge 4, and this is equal to the force of 1 on 4 plus the force of 2 on 4 plus the force of N on 4. These are all vectors, of course, and so what we've done is we've added the forces up by superposition. So we can take the sum of all the forces this way, and we'll say this is F subscript I. So this is the sum of all the forces on charge 4. Let's look quickly at a feature of Coulomb's law. So let's call it a characteristic. Because the force is an inverse square law, we can see that the force should decrease as distance changes. And also the force depends upon the charges, so the force will also change when the charges change. So let's look at what happens when the distance between two charges changes. Let's suppose that we have two charges Q1 and Q2 at the distance r as before, let's call this distance R subscript O. And suppose we double the separation between the charges. So this is Q1 and Q2 now. And we are saying that the distance now between the charges is equal to Rn, which is 2 times the original distance R subscript O. So we've doubled the charge. We can look at what happens to the force between the two charges. Let's say that the force of charge 1 on charge 2 is this force here, and the force of charge 2 on charge 1 is that force. So we can say that when we double the separation, the forces will change as we expect. So we can assume, or we can expect, that the force will be smaller because the distance is larger. So let's make this force shorter, and so we shall say this is the new force of charge 1 on charge 2. I put a prime on it, and this is the new force of charge 2 on charge 1 with a prime. So we can analyze this, and we know that the force according to Coulomb's law is equal to K Q1 Q2 divided by R subscript O squared. So this is the force between the two charges initially, and then after the distance is doubled, we will say that the new force F subscript N is equal to K. Again, we have the same charges Q1, Q2 divided by R subscript N squared, where R subscript N is equal to 2RO because we've doubled the original distance. So we can say that the new force is equal to K Q1 Q2 divided by 2R subscript O squared, which gives us 1/4 K Q1 Q2 divided by RO squared. And we will see then that this force F subscript N is just 1/4 of the old force that existed. So this tells us that when we double the separation between the charges, the force decreases by a factor of 4. And this is a feature of our inverse square law. So we can see that if we plot a graph of the force versus distance R, we should have a graph that looks like that, where we will see that suppose that we have R subscript O, and this force is given by F subscript O. If we double the separation to 2RO, this is not drawn to a very good scale, but the whole idea is that when you double the separation, the force should decrease by a factor of 4, and so on. And the same rule applies when you cut the separation in half, the force should increase by a factor of 4. When you cut the separation by a third, the force should increase by a factor of 9, and so on. So this is an important feature of Coulomb's law that should be remembered. So I'll stop here, and I'll go into examples of Coulomb's law in the next section.